Still admitting people. Professor Chaurasia is an assistant professor at the School of Public Health at the University of Waterloo, where he's been since 2015. His work focuses on the innovative application of statistical and computational methods in health research. And he's especially interested in data-related issues like working with incomplete or missing data, as we were just talking about, and as well as model selection. And his work spans a really broad range of topics, including youth and children wellness and pediatrics and cancer screening and care. So today he's going to be talking about multiple imputation. So Professor, please take it away.
Thank you. Again, thank you to everyone for organizing this, and you have my gratitude for inviting me for this talk. So thank you for that. So as my topic today, I'm going to talk about multiple imputation, and I'll talk about multiple imputation through a particular application, which is the lead exposure study, in which we are addressing issues of lead exposure in an environment that we are trying to see how it affected cognition or neurological function in children. So in the talk, I will sneak in what are the traditional methods of performing multiple imputation. Then I'll mention how they're limited. And through that limitations, I'll talk about my proposed methodology that is in a forthcoming paper. So my name is Ashok Chaurasia. I'm a PhD in statistics, and I'm an assistant professor in the School of Public Health Sciences at the University of Waterloo. And again, thank you for inviting me for this talk. So let's begin the topic by first giving a breakdown of how the presentation is going to go. We'll first introduce the application that motivated me to come up with this methodology. The second thing is we will talk about some of the data issues in that study and how those issues make the objectives inaccessible. And once we identify those issues and the objectives, the limitations of those objectives for that study, I will introduce how multiple imputation can solve those issues and help us assess those objectives. And once I introduce multiple imputation, I will sneak in my proposed methodology and say how it solves the second problem with that particular study. And once in statistics, it's or I would say in a quantitative field where we propose methods, it is traditional to run simulation studies where we show how well your proposed methodology works and we demonstrate its reliability. So I'm going to do the same in step 5. And once I have convinced the audience that this method is worth pursuing and can help a lot of applied researchers, I will talk about the several areas where the proposed methodology can help various applications. And once that I have shown that the proposed methodology has promise and can be easily adopted in several applications, I will use the proposed methodology to go ahead and answer the questions we had with the lead exposure study. And of course, I'll conclude the presentation with some closing remarks. So let's talk about the lead exposure study. So when we look at the lead exposure study, this was in a study where the researchers in 1971 in El Paso, Texas, wanted to investigate the amount of discharge a old smelter company was polluting the environment in which they were established. And the researchers wanted to figure out, because of this this discharge of tons of lead and other metallic waste in that area, the researchers wanted to assess the association between the lead exposure and neurological function. And the authors Landrigan et al. Basically collected data from a group of children that lived within 6.6 kilometers of that smelting company, whatever that was. So in order to assess this important objective, and it's a health objective, The authors collected variables from several various domains. One of the domains was medical history, another domain was neurological motor function, and of course, they collected some of the demographical variables, such as age and gender. So I specified the variables in the parentheses, but they will become familiar as we move forward through the presentation. And once they collected the variables, they categorized the subjects in the data set into two groups. One group was the lead absorption group that had 46 subjects, and the other group was called the control group, which had 78 subjects. The definition of lead exposure group was given by blood lead levels when they were at least 40 micrograms per milliliter in the year 1972. And the control group was a pure group where their blood lead levels were below 40 micrograms per milliliters. And these levels usually come about from researchers that do toxicology. So if people are interested in that, you can find literature as to why a 40 cutoff was used. And since this was in the 1970s, I'm sure those cutoffs have improved. But I use the cutoffs as that the original authors used. And the reason why I pursued their selection criteria or inclusion or exclusion criteria and their use of 40 as a reference is because my objective was to show that how their results, which were only using complete case analysis and were throwing out cases that had missing data, I wanted to compare their results to my results. So that's the reason why I pursued their models, even though I'm sure that can be improved. My improvement was in area of proposing a new statistical method. So in that particular study, there were variables of interest, a couple of variables of interest. So the first variable of interest is denoted by max FWT, and that basically denotes the number of finger wrist taps in the dominant hand of each subject. And this is one way of measuring neurological function. The second set of variables that we were interested in, that I call them exposure variables, because those are the variables I'm really interested in assessing in terms of the association with the outcome. And these variables are the blood lead levels in the years 1972 and 1973, and they're denoted by LD72 and LD73. In addition to these two, I have my first, which is the outcome. I have my exposure, which is the main predictor variable of interest or predictor variables of interest. We have control variables, age and gender. And I call them control variables because the idea is we want to take the impact of whatever age and gender are doing to neurological function. And we want to see after we control for the effect, what is the, how much variation can the exposure variables explain in the observed explain in the outcome. And that is the one of the objectives of interest. So given these are the variables in the model, the first objective that we're interested in is handled through simple linear regression. And I'm sure people in the audience are familiar with it. The idea here is we want to learn the strength of the association between age and neurological function when it is measured through the finger tapping wrist test. So we want to see what is the amount of the strength of association between age and neurological function and between those two groups. And one of the things I did in this model is I assumed parallelism. And again, that will become familiar when we actually go back to the example. So the idea is once we learn what is the strength of association and how they differ by the group, this is exactly what the original authors did in their paper, but they did not, they threw out 25% of their subjects from the data set because they had missingness. So remember, 25 subjects is 1/4 of the data. So I wanted to see that if I impute the data, how different will my results be? Now, the second objective with that study is something I introduced, is that I wanted to learn the association between neurological function and the nasty exposure to lead. And I wanted to see that strength of association after I have accounted for whatever age and gender does. So when you have age and gender in the model, they already explain some proportion of variation in the outcome. My objective was how much additional variation can be explained if I include the lead exposure in the model. And at the same time, I want to emphasize the importance of how much of this variation can be explained. And what you will see later is that when you impute the data, the imputed data sets will show the exposures explain more variation in the observed outcome compared to what the original authors, if the original authors had done complete case analysis, they would have underestimated how much lead exposure can explain neurological function. In this case, we know more the exposure, lower will be the neurological function value when measured through max FWT. So with these two models of interest, what we can do is we can perform CCA, which was the route that the original authors took. And I am going to, as a competitive, going to propose that I multiply impute the data and then perform these two models on the imputed data sets. So that's what I'm proposing, because I'm losing quarter of the data set if I perform complete case analysis. And if anyone knows a little bit about multiple imputation or complete case analysis, one thing you should always remember or recall is that complete case analysis almost all the time is going to give you biased results and unreliable results, and they're going to be inefficient. So complete case analysis is usually not preferred in real data sets. There are exceptions, but generally they're not preferred. More of the times they're wrong. So it's better not to pursue complete case analysis. So when we look at the given data set, what are the hurdles and how do they manifest themselves in terms of performing analysis or not being able to perform analysis? And what are the possible solutions once we recognize these issues with the data set? So the first issue is basically this block where I discuss missingness. The second block is the assessment of those objectives. So the first block is basically talking about how many cases are missing. So what we observe is that for the models that I talked about, if I were to run those models on the original data set, I would lose 20 to 30% of the observations in my data set. And that's a drastic proportion because it's somewhere between 1/3 and 1/4. 1/4 and 1/3, which is what we should be very mindful about, that a quarter of your data set is being thrown away. So I also gave the nature of where these variables are missing, but people can read it or we can come back to if people have questions. But the point is, when you have this substantial amount of data that is missing, one of the appealing methods for handling missing data is multiple imputation. Okay, so in order to handle the missingness issue, I'm proposing let's use multiple imputation. So we handle that issue. Well, we have the other issue is for the objectives that I mentioned earlier. Remember, the two objectives were SLR and MLR. In the SLR model, which is simple linear regression, I wanted to assess R-square. So when I said strength of association, that is another way of saying R-square. So I want to estimate R-square. Well, if I have imputed data sets, how do I get the R-square? Well, there are existing methods to get a combined R-square when I have imputed the data multiple times. But all those methods are either lack theoretical justification or are statistically unreliable. But those are the existing methods. So the existing methods that we have in order to estimate R-square are documented to be unreliable, which means we really don't have an answer. So I will propose a solution for under my new combining rule. The second issue is that if I wanted to conduct a partial F test, The reason I'm saying partial F-test is when I look at MLR, I take this sentence of learning about these two variables after accounting for these two variables. This tells me that I'm performing a partial F-test. So in order to perform a partial F-test, there is no literature in order to perform a partial F-test with multiple imputed data sets. So for these two issues, in terms of assessment, the solution is the new combining rule that I propose. Again, it has these advantages. We'll just skip over it because I don't want to lose the audience, but there are multiple advantages for the new rules, new method that I propose. Now, here is a visual display of the graph that the original authors presented when they collected data from that site. And this is a graph that I recreated. And what we see here is in the lead exposure group, we see that their average cognition value is lower than the control group, where the control group is a dot line. We expect this to happen because lead exposure has a negative impact on neurological function. And this is the estimates you would get if you use complete case analysis. So what we have to recognize here is that this R-square value is definitely an underestimate, okay? So once you recognize this, we're going to now talk about multiple imputation. So here, I'm going to very briefly talk about multiple imputation because it's a daunting task, but I'll try to make it simple. So the first step in multiple imputation is that you impute the data. You have an incomplete data set. So when you observe an incomplete data set, what you have are cells in these data sets, in this data set that are incomplete, they're missing. So the objective of multiple imputation, the first step is go ahead and fill those missing cells in your data set. So the act of filling in those cells is called imputation. But what we're saying is don't just fill in that cell in an informative fashion, in a modeling fashion. So in order to fill in those cells, we rely on an imputation algorithm. And in the imputation algorithm, you make certain assumptions. And these are some of the assumptions: that the data is missing at random, the semi-parametric approach or parametric approach, and you have to fully specify the conditional models. Again, I might lose some of the audience, so I'm not going to discuss, but the idea is that you're filling in those cells based on some model. And that model is using information existing in your data set, okay? And once I fill in the data set, when I fill in those cells, I create a complete data set. But I don't just create one data set, I create surrogates for those data sets. And in this case, in the Landrigan study and the data set coming from their study, I'm creating 1,000 possible copies of complete data set for the original study. Remember, the original study was incomplete, but I created 1,000 surrogates for it, where each of those surrogates has a different value filled in for that missing cell, okay? So we impute the data multiple times. That's why we call it multiple imputation. So the first step of multiple imputation results in multiple surrogates for the original incomplete data set, okay? And the good thing about this is that it preserves the same sample size as the original data set. So in none of these data sets will I lose those 25 to 30% of the subjects. So I preserve information. And from the financial perspective, I would say is that if you fund your study and you have 25 subjects that you're just throwing away, then for each subject you invested money, and that money is being thrown away instead of the information being used. So that's taxpayer money, and we should be mindful of that. So imputation in that way can improve the efficiency of a data set, even if it has missing values. So once you have imputed the data sets, now you can think of these 1,000 surrogates. You take each of these data sets and you perform your analysis, whatever analysis you're doing, perform simple linear regression, perform multiple linear regression, whatever it is, perform it and get the statistic you were interested in. So in my case, for that particular objective, I'm going to take each of those data sets. I'm going to perform my SLR or MLR, and I'm going to collect my statistics. So for example, if I got the R square, then I'll get R square from the first data set. I'll get R square from the second data set. I'll get R square from the 1000th data set, okay? So I collect my statistic of interest and I combine it. And once I collect the statistic of interest, I have multiple R square values. Now the question is, what is the unique R square value for my data set, which was originally incomplete, that I imputed? So in the third step, what I'm trying to do is that once I have the statistic of interest, then I somehow, and I have multiple copies of it. By copies, I shouldn't say copies, I have multiple estimates for it. I need to somehow get a universal R square, one R square value for one data set. So the third step, obviously, then is that you take all the statistics that you collected and you combine them. So when you combine, and that's why they're called combining rules. So when you combine these statistics, the bane of existence of doing parametric statistics is that you have to assume distributions. So if you're doing parametric frequentist methods, in order to combine those statistics, there is this assumption of normal distribution, okay? So in order to combine them, if they're approximately normal, you can use these beautiful formulas to combine them, okay? But these combinations make sense only if the thing you collected tends to have a normal distribution. And we know that not everything in the universe is normally distributed, okay? So the hurdle is this. So when you look at the 3 steps of imputation, the first step is I impute my data set. For my study, I have done that. That's easy. Well, relatively speaking, it's easy. The second step is I took each of my data sets and did my analysis. Well, I'm happy with that too. The issue is now going from step 2 to step 3. In my case, the things that I collected are not normally distributed. They are distributed in some other distribution, such as beta or F. So in order for me to combine them, I can't combine them because they're not normal. So how do I go from step 2 of MI to step 3 of MI? Because I can't just apply this because they're not normally distributed. Well, that's where my proposed method comes in. So what I do is I say, take those things that we collected from each of the data sets that we know are not normal. I take those things, subject them to a transformation that brings them to approximately normal. So once I transform them in stage 2, then I can combine them using the step 3 methods, okay? Again, don't worry about the formulas. Hopefully my intuitive way is helping people understand. So if you transform it to normal, and then you can easily use step 3 and combine it. So once you combine it, you can go ahead and get the statistical inference. After you transform it, you can get the statistical inference using this statistic. So that's the proposed methodology. Between step 2 and step 3, I included a sub-step, okay? So as I said, in statistics, the idea is that whenever we propose a new method, we provide a theoretical justification. So the theoretical justification is what you have seen here about the satisfying the normality condition. So now I need to convince an audience that if they were using this method in some simulated data sets, how well does it perform? The idea about a simulated study is that I know exactly the true nature under which the data set was created. So I know the truth. So if I do propose a method and perform a statistical analysis, I can compare the result of my statistical result with the truth and see how good or bad that is, okay? So I give the nature here is that I took my data set from the linear regression setting, and I introduced a special kind of structure in there. So when you look at this left-hand side, all it is saying is that, look, this data set has no signal in it. There's no worth, there's no point about performing a regression. The second universe in which I created the data set, I say that there is some kind of signal in there and you need to capture it, okay? And I looked at those two settings under different configurations where the sample size increased from relatively small 20 all the way to 100. And I took a more complicated setting where sometimes the maximum number of predictors is 3. And in the other setting, the maximum number of predictors was 5. So I have created, let's see, 20 universes here. Basically, I'm creating data sets from 20 different configurations and seeing how well does my method work, okay? And when you look at the setting, again, this is a bunch of blabbering statistical stuff. We can come back to if people want to investigate it, but all it says is that take any one of these universes where a data set is created. I introduce missingness in them because I'm dealing with missing data, and I perform my 3 steps. This is step 1 of imputation. This is step 2 of imputation. This is step 3 of imputation. And then I repeat this process 1,000 times. So technically, I have created here 15,000 data sets, and I'm testing my method in all these data sets and how well they work, okay? That's what the simulation does. So what is the takeaway? I need to be mindful of time. So the figure on the left that you see this is the scenario where there is no signal whatsoever. There's no need to build a regression model because there's nothing there, which means is that there is no signal there, which means most of the time, if I do say there is a signal, I should say that less frequently. For example, since there is no signal, I shouldn't be saying that I'm 100% of the time saying there's no signal. Sometimes a test will make a mistake. And if people remember when you perform statistical test, you know the 5% thing. We say a test we're using an alpha or significance level of 5%. So in this universe, I should be wrong at the most 5% of the time. So when you look at this 5%, you see a shaded region. The shaded region is basically the region of indifference of 5%. So in this universe, the method that I proposed is called Hodgins. And the traditional method, which is the old way of combining things, is basically this golden color and the pink color. So a good method should remain in this band, in this universe. So the only methods that remain in that band are the traditional methods, which is the golden one and the pink one. And the one that lives in that band is the one that I proposed, which is the Hodgins. So basically, my proposed method, which is computationally less cumbersome because it only deals with scalar entities and does not deal with matrices, it lives within that band. And these 3 methods, basically the golden, the pink one, and the red one, are basically competitive methods. On the right-hand panel, what you see is we know they are competitive. Now, which one is superior? When you're trying to show that your method is good, you don't necessarily need to show superior. What you can show is that the method I proposed is equivalent to the traditional methods, where the traditional methods are cumbersome. But the method that I propose is computationally very convenient, okay? So we can see it has similar levels. And when you compare the 2 graphs, what you should recognize is that as I increase the percentage of missingness, you should not expect a miracle with any test. The reliability of any test will will decline as percentage of missingness increases, okay? And missingness is a word in statistical literature dealing with that topic. And so what the take home message is that the proposed method without any of the computational burden is equivalent to the traditional methods that are computationally cumbersome, okay? Because they deal with matrices and you have to find inverses of matrices in higher dimensions. And you can see a similar pattern as I go from increased sample sizes. You can consistently see the three methods live within this band, and those three same methods have similar power. And this consistently happens as I increase sample size, which is a good sign that the method I proposed is statistically provides the same inference as the traditional method, which is cumbersome, okay? And even when I complicate the model with 5 predictors, the similar kind of story comes about again, again, and again. So through the simulation in this 15,000 universes, I have shown that the proposed method is working really well with all the benefits and with less of the negatives, in a sense, using calculations involving matrices, okay? So now that I have convinced through simulation that the method has a lot of promise, here are some extensions of the proposed method. So the idea is, in the traditional way of doing things with MI, none of these tests are possible because they deal with these complicated vectors and matrices. Because my method doesn't rely on those vectors and matrices, now I have, just for example, 6 new tests that now become available to any researcher who'll be using them in their application, okay? So that's the idea, where the simple methodology that I proposed has a lot of options to expand and help researchers in applied fields if they're using any of these tests. And these are just some examples. So that's the take-home message from those simulation studies. And near the end of the presentation, I'll go back to the example that motivated this whole study, this whole research objective. So we go back to the figure on the left panel, which you saw before, but that figure was under complete case analysis, where you threw out 25% to 30% of your subjects. Then on the right panel, I have its version when I impute the data set. So what you'll notice here is that when you look at, you'll see a couple of dots here that I call them the push pin symbols because they look like push pins. Those push pins are actually the observations you lost that the left panel ignored. So those subjects were thrown out, whereas in the right panel, I am using them in order to estimate that regression line. So when I use them, what happens is that when you look at the left panel, you can see the R-squares around 35, 31 and 45. Again, I don't care about the specificity of the number. I care more about the difference. So when you look at the new method that I proposed, you can see that in each of the exposure groups or each of the groups, the R-square has increased by 15%. That is a substantial increase. This tells us that the estimates from the original study are definitely downplaying the importance of age and how it contributes to cognition, okay? And how it is associated with neurological function. I keep saying cognition, I apologize for that. But you can see a reduction by 15% if you perform complete case analysis. And then again, there are numerical results, but we can skip over that. The second objective was that I wanted to see how much does lead exposure contribute to R-square after accounting for the impact of gender. And now again, this is a statistical notation. If it bothers you, just don't look at it. But the idea is, how much more can lead exposure explain the variation in my outcome? So here are 2 kinds of histograms. What you see here, you can just focus on the histogram on the right panel, is that if you use complete case analysis, you will say that lead exposure explains around an additional 8%. If you use the multiple imputation method, you're going to say that lead exposure actually explains 9% of the variation. This means that if you use complete case analysis, it will downplay the negative impact of what lead exposure does to neurological function. And you have to, that is what we need from a public health perspective. That is a crucial message that needs to be sent out, or that needs to be communicated to an audience, that if you use complete case analysis, something that is very harmful, the extent of how harmful it is will be downplayed. So you need to be very mindful of that. And this is a very good example where multiple imputation can highlight that, okay? And so what are the contributions and final remarks? Is that the method that I proposed is only based on one-dimensional entities instead of the traditional methods that always involve vectors or matrices, and these vectors and matrices can be of large dimensions if your objective, depending on your objective. If it is of larger dimension, then they will become more and more unreliable because you're playing with higher dimensions. And one of the other things is that the traditional method makes an assumption, which is called proportional and equal loss of information. I just put this here hoping that someone in the audience would be familiar with this, is that this is an assumption that is always made in the traditional method, and because it involves matrices. Since my method does not use matrices and is always univariate, I will never need to rely on this assumption. And the problem with this assumption is we can never verify it. In no setting can be verified, which means you have to blindly follow it if you use the traditional method. The second advantage is that the proposed method had nominal statistical inference as the traditional methods. That's the other message, take-home message from the proposed methodology. The third advantage is this is for computation, people who do computational science. What you have to understand is that in matrices, in order to get a number, you'll have to perform 3 operations. And because you're playing with matrices, it becomes OP3, which means you have to do 3 tasks in order to get a number. Well, in my traditional method, you just have to perform 1 task and get that same equivalent number. So in terms of computation, this is huge. If you're dealing with large data sets, if you're dealing with inferences or hypotheses that are in large dimensions, computationally, you gain a lot of computation time. For example, instead of your code taking an hour to run, you'll only take probably 6 minutes instead of 60 minutes. So from computation, that is the benefit of using the method that I proposed. And the last step is basically that the method that I proposed can easily be adopted in any application that intends to use multiple imputation. All you do is, again, I'm saying all you have to do, it's easier said than done. But I mean is that it can easily become a sub-step between 2 steps, and you can then use the existing machinery or existing code and let it run its course and give you a reliable statistical outcome or inference without any of the computational burdens, okay? So with that, that's the end of my presentation. And if there are some references, no one can probably see because of the font size, but I'll stop there and open the floor for questions if people have any.
Fantastic. Thank you very much for sharing. Very interesting. I know it's always a challenge to know you have some imperfect data and you still want to make some kind of use of it. So this is definitely an interesting option. Our first question is always the same. It's mostly so that Rohan can go and get himself even more books. And it is, what kind of book or what title would you recommend everyone reads?
There is a very, it's a novel, I guess. Okay. I read it when I was an undergrad and I love that book. So the book is called Barefoot Heart. and the author is Elva Trevino Hart. And it's a very good story about from a child and she's and how they migrate from Mexico to Texas, and they talk about what the migration, how it helped them see different things. And so for me, it was, being a migrant myself, it was very nice, nostalgic kind of. So I love that story. It's very genuine, it's very sweet, and you can see how some of the opinions of the child, how they grow and how they recognize some of the troubles that their parent faced, and how they were able to get an adult perspective on it when they became adults. So it's a very, very heartwarming book that I would recommend. So it's called Barefoot Heart. Maybe I'll type it in chat.
Yeah, I've never heard of it. It sounds,
Yeah,
thank you so much, Thomas. Always on top of it. Sounds fascinating.
Yeah, it's a
I have to say, that was not what I was expecting, but that sounds awesome. Thanks for sharing.
Elva Trevino Hart.
So we'll stop recording now.